Now we may start. Good morning, good afternoon, or good evening, everybody. Welcome to week 15 of our focus program. And we start with lectures by Michael Hartz from Saarland University on the Drury-Arveson space. Michael, please.
Well, thanks, Javad, for the introduction. And actually, thank you to Javad and Ilya and Damia for organizing this whole focus program. I've really been enjoying it. And I think it's also very good for the field to have so much activity over a course of several months. So thanks a lot for that. Also, thanks for inviting me to give these talks, and thanks to you for coming to them. So yes, I'm going to talk about the Drury-Arveson space. And let me begin by giving you sort of a very rough overview of what I'm going to talk about. So I'm going to denote the open unit ball in C to the D by BD. So this is just the set of all vectors in CD which have a Euclidean norm strictly less than 1. Right? And then sort of very informally, you can define the Drury-Arveson space, or you can say that the Drury-Arveson space is a space of holomorphic functions on the unit ball, which in some sense generalizes the classical Hardy space H2 on the unit disk. So we had sort of the first week in this program was a week on the Hardy space by Javad, and I'm going to try to convince you that this Drury-Arveson space is a reasonable generalization of this Hardy space to several variables. By the way, if you're worried about this this word here, holomorphic functions on the ball, if you're not so familiar with several complex variables, don't worry about it. If you just work in on the unit ball, a lot of these non-trivial phenomena like extensions never appear, and you can just take as your working definitions power series that converge on the open ball. So just think of power series if you like here. So convergent power series on the ball. Okay, so why do people study this space? Well, if it's a reasonable generalization of the Hardy space, then okay, it's reasonable to look at it. But there are actually deeper reasons. And in these lectures, I'm going to focus on two reasons, one operator theory and one function theory. So the operator theory reason is that on this Drury-Arveson space, there is a distinguished tuple of operators which generalizes the unilateral shift to several variables. So right on the Hardy space, you have multiplication by the variable, which is nothing else than the unilateral shift. And this plays a crucial role in the study of operators on Hilbert space, especially contraction operators. And there is a version of this on this Drury-Arveson space, which plays a similar role for certain tuples of operators. They're called commuting row contractions. And I'll make this precise. And so the second reason, which essentially comes from function theory, is that this space is an example of a very particular class of Hilbert function spaces called complete Pick spaces. And it's more than just an example, it's a universal such space. So amazingly, this space plays two universal roles. It plays a universal role in operator theory when you study these row contractions, and in this study of these special Hilbert function spaces. So in my opinion, either one of these reasons would be good enough to look at this in great detail. But we actually have both of these reasons. Okay. So this also sort of gives a rough plan for my lecture. So I'm going to start by trying to make this definition precise, and then I'm going to talk about the operator theory aspects, and then I'm going to talk about the function theory aspects. Okay, that's the plan. Okay, so where can you learn more about this? I thought I'd give you some references, but I only wanted to give you a very short list. So I only picked out 3. So apologies if I left out your favorite paper on the Drury-Arveson space. But the first thing I want to highly recommend is this survey by Or Shalit, Operator Theory and Function Theory in the Drury-Arveson space and its quotients. So everything I'm going to talk about that happened before 2015, which is essentially when this paper appeared, is covered and explained very nicely in this survey. So I highly recommend looking at that paper. Another survey, which I also recommend, is due to Shelley Fang and Jingbo Cha, where they, so this is from 2019, and you can find some of the more recent material in there. And then for this second motivation to study the space, so this these complete Pick spaces, the book on the subject is this book by Agler and McCarthy, Pick Interpolation and Hilbert Function Spaces. And so the reason why the Drury-Arveson space comes up there is explained in a lot of material surrounding this. Okay, so these are three places you can look at. The others, but I think this is a good place to start. Okay, so when I prepared for these lectures, I looked at some of the early papers where the Drury-Arveson space appears. And so it has its name from two papers in the area, one by Drury in 78 and one by Arveson in 98. And so Sam Drury was interested in extending von Neumann's inequality to certain tuples of operators. And he realized that you can do this on this space, which is now called the Drury-Arveson space. Of course, he didn't call it that. And he also proved some version of a dilation theorem. And then this 98 paper of Arveson was very influential. He proved sort of a better version of Drury's theorem, a lot of theorems surrounding it. And in particular, he also put this space really into context. So as far as I can tell, he was the first one to actually realize that it's a reproducing kernel Hilbert space. He computed the reproducing kernel and showed that it's something meaningful. And he also connected it to a symmetric Fock space, which I'm going to mention later. So the space got its name from these two papers, but the other papers where it appeared as well. So here's just some selection of them. So there are actually two earlier papers by Lubin, one from 76 and one from 77. The first one, 76, in that he also proves a version of a dilation theorem. And knowing what we know today, you can sort of see that it actually gets pretty close to Drury's and Arveson's dilation theorem. And in the 77 paper, he was interested in subnormal operators. And so he used the Drury-Arveson space to give an example of two commuting subnormal operators whose product is not subnormal. Then there is a 93 paper by Müller and Vasilescu where they prove a whole scale of dilation theorems, and the one for the Drury-Arveson space is one of them. And then let me just mention three more papers. So two which are related. So one by Davidson and Pitts and one by Arias and Popescu, where they come to this space from a non-commutative point of view. So this is closely related to what Mike Drury talked about last week when he talked about the NC Hardy space and what happens if you take NC functions and restrict them to commuting variables. And yeah, so I should say that the dates here are a bit fuzzy. I mean, I think these are publication dates, but these two papers cite each other. So I assume they were written around the same time. And then there are two papers in 2000 by Agler and McCarthy where they come to this space from studying certain interpolation problems. And I'll also say more about this. And afterwards, this really exploded, and it's hard to keep track of how many other things appeared. So I'm going to leave this at the three dots at the end. Okay. So you can also see in comparison to some of the other spaces that we covered in this focus program, this one is comparatively young, right? I mean, it's certainly much younger than the Dirichlet space or the Bergman space, for instance. Okay, so what is this Drury-Arveson space then? Well, I thought instead of just writing down the definition and then trying to convince you afterwards that it's something reasonable, it might be fun to try to come up with a definition ourselves. So before we do this, let me remind you of the Hardy space on the disk, right? So this is, after all, this Drury-Arveson space is supposed to be a generalization of H2 to several variables. So let's look at H2 again. So we've seen this in many talks, but just as a reminder, you can define it to be the space of all holomorphic functions on the disk. So this curly O is holomorphic functions, right? So you might also want to write it like this. So all holomorphic functions on the disk whose L2 norms over circles centered at the origin, when you take them with respect to arc length measure, are bounded. And there's also a description in terms of Taylor coefficients. So it consists of all holomorphic functions whose Taylor coefficients are in little L2. And we also know that it's a reproducing kernel Hilbert space. So this means that point evaluations are continuous. And so they're given by some inner product against some vector in the Hilbert space. And this vector has a very nice form here. It's the Shager kernel, which is 1 over 1 minus ZW bar. Right? So the point is, if you take a function in the Hardy space and you take the inner product against the kernel, so the function that you get by fixing the second variable to be W and letting the first variable run, then this reproduces the value of your function at the point W. Okay. So how can we come up with a generalization of this, this space to several variables? Well, I should acknowledge that there is a generalization, which is appropriately called the Hardy space on the ball. And you get this generalization just by taking the first definition above, so that the function theoretic definition, and replacing arc length measure with surface measure. So the surface measure is the unique probability measure on the sphere, which is invariant under unitaries. So d by d unitaries. And then you can just copy this definition essentially, right? You just say all holomorphic functions on the ball for which these L2 norms, but now you compute them with respect to surface measure, stay bounded. And this is certainly a very reasonable thing to do. But it turns out that this space doesn't quite play the role that the Hardy space plays in one variable, for instance, in operator theory. It doesn't work out to be the same thing. And the actual reasons for why this happens are, and maybe I cannot explain them in one line, but let's do a one-line computation, which is supposed to convince you that maybe the relationship between the one variable Hardy space and this Hardy space on the ball is not as tight as you might hope. And so to see this, let's just look at what the norm of let's say Z1 to the n is in this Hardy space on the ball. Right? So in the Hardy space on the disk, the norm of Z to the n is always 1. If you do this in the Hardy space on the ball, well, then you have to compute this soup here. But if you just do it for monomial, it's easy. The r to the n, you can pull it out, and then the soup is just attained at r equals 1. So this is nothing else than this integral over mod Z1 to the 2n. And then, well, you can compute the integral explicitly. But you don't even have to, because even if you don't compute anything, you can see from the dominated convergence theorem that this tends to 0 as n goes to infinity, right? Because the margin of Z1 is equal to 1 on the one-dimensional circle, and it's strictly less than 1 everywhere else. And so this one-dimensional circle, as soon as D is at least 2, is a null set, and so by dominated convergence, this tends to 0. So this shows that, well, it is true that if you plug in D equals 1, then you recover the Hardy space on the disk. But you don't recover the Hardy space in the disk in the strong sense that if you take a function that just depends on one variable, let's say Z1, then the norms are the same. So I want to use this as a sort of motivation for coming up with a Drury-Arveson space. So suppose we try to do this. So our goal is now to find a Hilbert space of holomorphic functions on the ball, which satisfies 3 things. So the first thing is what I just discussed. If you have a function of a single variable, let's just say Z1, then the norm is really then the norm in H2. So in other words, if f is g of Z1 for some H2 function g, then I want f to belong to the Hilbert space, and I want the norm of f in the Hilbert space to be the same as the H2 norm of G, right? So now I want to really recover H2 in one variable, or in other words, I want to have an isometric embedding of H2 in this space. Okay. Then the second property I want is that the space should reflect the underlying symmetry of the domain. So I want, if I take a d by d unitary matrix U and a function in the space, then the composition should be again in the space, and I want the norm to be the same. I think that's fairly reasonable. If you think of the Hardy space on the disk, right, that's invariant under rotations, and I just want the higher variable n log of this. And mostly to make my life easier, I will also want to assume that the polynomials are dense in this space. So there's some flexibility in these assumptions. Well, of course, there's nothing special about Z1 in the first assumption, because if you have unitary invariance, you can replace it by any other Zi. Also, one really says that you have an isometric embedding of the Hardy space. If you like, you can turn the arrows around and you can say if I take a function on the ball and I restrict it to a one-dimensional slice, then I want to recover Hardy space in this way. That also works. I decided to go with 1 because most people find subspaces slightly more intuitive than quotients, but it doesn't matter. And 3 actually, under some mild assumptions like boundedness of point evaluations, actually turns out to be automatic, but I want to assume it so that just to make my life a bit easier. Okay, so the claim is if I take these 3 things, then there's a unique space that satisfies these 3 things, and this turns out to be the Drury-Arveson space. Okay, so let's try to see if we can come up with what this space is going to look like. So the first we need some notation. So just like in multivariable calculus, we're going to use a multi-index notation. If I have a multi-index alpha, then I'm denoting by z to the alpha to be the product of the individual zi to the alpha I, so the usual monomials. Alpha factorial is going to be the product of the factorials of the entries, and the absolute value of alpha is just the sum of the entries. Right? So this is the usual multi-index notation. Now, the claim is that the monomials z to the alpha have to form an orthogonal basis because of unitary invariance, essentially. Well, I mean, the linear span of the monomial is dense by assumption 3, and I claim that distinct monomials or different monomials are also orthogonal. So let's have a quick look at why this is the case. So suppose we have 2 multi-indices alpha and beta that are different, and then without loss of generality, let's say they're different the first entry. So let's say alpha 1 is not equal to beta 1. And then what you can do is you can look at a unitary ut, which is e to the it in the first slot, and then you just have 1s down the diagonal. Okay, and then you use unitary invariance, because then if we compute z to the alpha in our product z to the beta, then by unitary invariance, this is the same as z to the alpha composed with ut in our product z to the beta composed with ut. And if you think about what this composition does, well, z to the alpha composed with ut is going to be e to the I alpha 1 t, and similarly for the beta. So here we get e to the I alpha 1 minus beta 1 t z to the alpha in our product z to the beta. And now you integrate in t. And if you integrate from 0 to 2 pi, then you get that the right-hand side is equal to 0, and the left-hand side is 2 pi times the inner product. So the inner product has to be 0. Right? This is the usual. So you integrate from 0 to 2 pi. And then you get that the different monomials have to be orthogonal. That's the usual argument. Okay, so the monomials form an orthogonal basis. And so all we need to figure out is what the norm of z to the alpha should be. And then the space is uniquely determined. So let's try to do this next. Let's clear this. Okay, so what should the norm of z to the alpha be? Well, there are multiple ways to work it out, but here's one of them, which uses essentially reproducing kernels. So the idea is we're demanding that all functions of a single variable that come from H2 functions are in the space. So in particular, we can do this with the Schegel kernel. So we take 1/1 minus lambda bar z1. This has to be in the space by assumption. And let's work out what the inner product against an arbitrary power series f is going to be. Well, we just worked out that different monomials have to be orthogonal. So if you just expand everything into a power series, then you get this sum n equals 0. So the only thing that survives are the coefficients of z1 to the n on the left. So what you get is the sum a n 0 0, and then you get lambda to the n from the kernel, and then you get the inner product of z1 to the n with the z1 to the n. All the other coefficients, all the other inner products are 0. But we defined it so that this is equal to 1, right? Because it should look like the Hardy space in one variable. So this is nothing else than f of lambda times E1, where E1 is the first unit vector. So this looks pretty promising, right? Because this says that if you take the one variable Sego kernel, and you take the inner product against it, then you reproduce the values of your function, well, at least along the first coordinate axis. But then we have unitary invariance, so you can move around this lambda E1 over the whole ball. So if you have an arbitrary point W in the ball, you can find it d by d unitary, let's say, so that U star W is of the form lambda E1, right? You just move it into the first coordinate axis. And then if you apply this, this thing we just worked out to F composed with U, then on the one hand, you can see, so F composed with U of lambda times E1 is F of W, because U of lambda E1 is W. And so you can use unitary invariance to move this unitary to the other side as a U star. And then you just have to work out what you get. And to work out what you get, you should really think of this thing as now looking like 1 over 1 minus the inner product of Z with lambda E1. And so if you think about it this way, if you pre-compose with U star, you have to write a U star Z, you move the U on the other side, and then you get this thing on the right-hand side. So this thing. All right. That's also meaningful because this means that if this scheme is going to work, then this has to be a reproducing kernel Hilbert space. And this formula here will be the reproducing kernel at the point W. So I'm going to get back to this in a minute. But let's now work out what the norm of Z to the alpha is going to be. So you can apply this identity here with F equals Z to the alpha. Then on the one hand, you get W to the alpha is the inner product of Z to the alpha against the kernel. And then you do the same thing again, you write everything out in power series. So if you write this, first you do the geometric series. So this is ZW to the N. And then you can expand the inner product using the multinomial theorem. So this is sum over N. And then the sum over, well, I guess I should use beta now. So all multi-indices beta of length N. And then I get these multinomial coefficients, beta factorial times Z to the beta W bar to the beta. And then I use again that monomials so distinct monomials are orthogonal. So the only thing that survives in this thing is the coefficient of Z to the alpha, which turns out to be, so this is this mod alpha factorial divided by alpha factorial, W to the alpha. And then you're left with the norm of Z to the alpha squared, right? So this is true for all W. So this tells you what the norm of Z to the alpha has to be, right? Because then the conclusion is that the norm of Z to the alpha has to be alpha factorial divided by absolute value of alpha factorial. Well, that the norm of Z to the alpha squared. And we already worked out that different monomials have to be orthogonal. So this uniquely determines a space. And so we're going to take this as our definition. We're going to define the Drury-Arveson space now as the space of, well, for now, formal power series, so that the coefficients are in some weighted L2 space, and the weights are the ones we just came up with, right? These alpha factorial divided by absolute value of alpha factorial. Okay, so right, this, I mean, if this, we still have to convince ourselves that this works, but this was sort of forced upon us by this requirement that we have unitary invariance, and in one variable it looks like the Hardy space on the disk. So usually when you define this, it's, you know, sometimes people object why do the weights look the way they do, and there are multiple ways of motivating these weights. The motivation I just gave you is essentially it comes from the geometry of the underlying domain. It comes from unitary invariance on the ball. All right. So if you do this, then, well, we don't just get formal power series, just like in the case of the Hardy space. You can use Cauchy-Schwarz to work out that these power series actually converge on the ball, and you get a pointwise estimate, which should look familiar from Hardy space theory. So these things actually converge uniformly on every ball of radius strictly less than 1. And so they are actually holomorphic functions on the ball. And we have continuity of point evaluations. Okay. So now if you read the argument I gave you on the previous slide backwards, then this argument tells you that if you define the Drury-Arveson space this way, then the reproducing kernel has this form. So this is the same formula we saw earlier, And if you take this above now as the definition, then you have to read the argument backwards, but it's the same computation. So we get a reproducing kernel Hilbert space of holomorphic functions, and the reproducing kernel is this guy. And so knowing that this is the reproducing kernel also shows that the space is really unitarily invariant, because this kernel is clearly unitarily invariant, right? If you look at K, U, Z, U, W, where U is a D by D unitary, then this is the same thing as K, Z, W. And so if the kernel is unitarily invariant, then this gives you that the whole space has to be unitarily invariant as well. And so this thing really fits the bill. This space is the unique space that looks like Hardy space in one variable and is unitarily invariant. By the way, you can also take this proposition as a definition. So you can just define the Drury-Arveson space to be the reproducing kernel Hilbert space with this kernel. And the way this works is you can convince yourself that this function is a positive semi-definite function on the ball. And so you can evoke the Moore-Ehrenstein construction that there has to be some space of functions whose reproducing kernel is this function. This is also a fine definition, and it also makes sense in some way, because this is the most obvious generalization of the Hardy space kernel to the ball you could write down, right? If you compare this to the kernel of the Hardy space, the Zego kernel, it was this function. So you just replace ZW bar with this inner product. Okay. So that's the definition of the Drury-Arveson space. Now, for the Hardy space and the Dirichlet space on these other spaces, they weren't just defined in terms of power series. There was a function theoretic description. And so let me talk about that for a minute. So I want to compare this space to spaces on the ball that have a function theoretic description. So one possibility would be the Hardy space on the ball. But it turns out that the computation is slightly nicer if you take the Bergman space on the ball. And so that's just as well. So let's take the Bergman space. So just to remind you, the Bergman space consists of holomorphic functions whose, holomorphic functions that are in L2 with respect to volume measure on the ball, right? So we had a whole week on mostly on the one variable Hardy space. The mini course was given by Stefan Richter. And so this is the obvious generalization to the unit ball here. And in particular, this is a pretty concrete function theoretic description. L2 norm is finite. So let's try to compare the Drury-Arveson space to this space. And to make my life a bit easier, let's assume we're in dimension 2, right? This is the first thing where things look kind of different. So the Bergman space is also unitarily invariant. So by the same argument I gave you earlier, monomials form an orthogonal basis of the Bergman space. And one can compute the norm. It's a little tricky, but you can work it out. You can actually compute this integral, and what you get is this formula here. So we see our familiar weight that we had in the definition of the Drury-Arveson space, and then there is some extra factor, which at least if alpha is non-zero, is comparable to 1 over absolute alpha squared. So the norm of a monomial in the Bergman space is smaller by a factor of 1 over absolute alpha than the norm in the Drury-Arveson space. So in other words, the norm in the Drury-Arveson space is bigger by a factor of the degree than the norm in the Bergman space. Okay. Now the point is that this factor mod alpha actually has function theoretic meaning, and you can get this factor by looking at the radial derivative. So the radial derivative of a function f is what you do is you take the derivative with respect to one of the variables, you multiply by the variable again, and then you sum the whole thing up. And it's easy to work out that if you apply the radial derivative to z to the alpha, then you just get absolute alpha times z to the alpha, right? Because the point is, if you take the derivative for the jth variable and multiply by zj again, then it just gives you alpha j times z to the alpha, and then if you sum over all of the variables, then you get the absolute value of alpha. So in other words, this is saying that the norm of a monomial in the Drury-Arveson space is comparable to the norm of its radial derivative in the Bergman space. And so if you put all of this together, you see that a function is in the Drury-Arveson space in 2 variables, if and only if its radial derivative is in the Bergman space in 2 variables. and you get equivalence of norms. Well, you have to be a little careful because this doesn't work for the constant functions, right? The radial derivative takes constant functions to 0. But as soon as you add the value of your function at the origin to this, then you get an equivalent norm on the Drury-Arveson space in dimension 2. Right, so this computation works if d equals 2, but hopefully you can believe that if you're a little more careful, then you can make this work in higher variables. And so let me just tell you the result that you get if you work this out in higher variables, and it's the following theorem. So what you have to do is you have to take an integer m, so this is how many derivatives you take, and you want m to be so big so that 2m minus d is bigger than -1. And then the Drury-Arveson space consists of all holomorphic functions on the ball, so that the mth radial derivative is in L2 with respect to this weight here. So the condition 2m minus d bigger than -1 just guarantees that this weight is integrable. So this makes sense. And also you have equivalence of norms. So the norm of a function in the Drury-Arveson space is comparable to, well, once you add the value of the origin to this L2 norm of the radial derivative. So this formula, it becomes cleanest if d is even, because if d is even, then you're allowed to take m to be d over 2, and then this weight here just becomes 1, so you don't have to worry about it. And then you get this pretty concrete description. So you have function is in the Drury-Arveson space if d dimensions, if d is even, if and only if d over 2 radial derivatives belong to the Bergman space. Okay. This suggests a heuristic, namely, if you do function theory, the Drury-Arveson space behaves more like the Dirichlet space than like the Hardy space in one variable. This is maybe not so obvious from the way I motivated it, right? If you think about it as, well, it looks like the Hardy space in one variable and then you add unitary invariance, then it sounds like maybe the function theory is like in the Hardy space. But because you have this derivative here, the function theory actually turns out to look more like the function theory in the Dirichlet space. So in particular, if d is 2, right, then the condition is really that one radial derivative belongs to the Bergman space, which looks a lot like the definition of the Dirichlet space. And we're going to see some instances of this behavior later on. I also want to mention that these formulas that I have above here, they're not exact in the sense that they're not equalities, right? They're just equivalences of norms. But you can actually work out an exact formula, a function theory formula, if you're a little more careful. So you have to modify the definition of the radial derivative. And so this is actually done in a recent paper by Accozzi, Mangozzi, Peloso, and Salvatore. So if you want to have a formula where there are no hidden constants, you can look at that paper. Okay. Now, this is also a good place to mention that the Drury-Arveson space belongs to a whole scale of spaces, and you can index them in various ways. I've indexed them now here by a real parameter a, and I've chosen the index so that Drury-Arveson space sits at a equals 1. And in this scale, then at a equals 0, you have the Dirichlet space, and at a equals d, you have the Hardy space on the ball, so the one I mentioned at the very beginning. And at d plus 1, you have the Bergman space on the ball. So you can see if d is 1, then the Drury-Arveson space and the Hardy space collapse as they should. But if d is bigger than 1, then they move apart. And also in this picture, for what it's worth, the Drury-Arveson space, at least for large d's, it's closer to Dirichlet space than to Hardy space. So how are these spaces defined? Well, just like in the Drury-Arveson space, there are multiple descriptions. At least if a is bigger than 0, you can just write down the kernel. That's usually the quickest way of doing it. And you take the Drury-Arveson kernel to the a. If a is equal to 0, you have to take logarithms instead of powers, but I'm not writing it down here. There's also the power series characterization. So a function is in such a space if and only if something that looks like the Drury-Arveson space norm, but now includes an additional weight here, is finite. And both of these descriptions also suggest, at least to my mind, that the Drury-Arveson space plays a distinguished role in this scale, because it just happens when you take the power to be 1, or when you take the weight to be equal to 1. So that seems pretty natural. And there's a function theory description, which I'm just going to mention in passing, but so it kind of looks like the Drury-Arveson space definition, but you have to adjust the weight up here depending on which place in the scale you're at. Either one of the power series definition or the function theory definition also shows that you have inclusions, right? So if A gets bigger, then the weight in the power series definition gets smaller, so the norm gets smaller, and therefore the space gets bigger, the bigger A gets. So we have inclusions this way, right? And you can also see it in this function theory definition fairly easily. So the Drury-Arveson space is contained in the Hardy space, and in particular in the Bergman space. Okay. All right. Now, in the Drury-Arveson space, there is another picture which turns out to be extremely useful, and this is the non-commutative approach. So Mike Drury last week gave a lecture series on non-commutative function theory, and in particular he talked about the NC Hardy space, and he also mentioned how it relates to the Drury-Arveson space. So I want to recall some of the things that he said, because there are one or two points that I want to make in how this relates to the Drury-Arveson space. So as Mike explained last week, you start with a d-tuple of freely non-commuting indeterminates. So these are variables, but we're not assuming that x1, x2 is the same as x2, x1. And then if you want to form things like polynomials or even monomials, just what you should do is you should look at the free monoid on d letters. So this is the set of all finite words in the variables 1 through d, and the empty word is allowed. And if you have such a word in these letters 1 through d, then you can form the corresponding monomial, which I'm denoting by x to the w, just by picking these non-commuting indeterminates according to the entries of your word. And as Mike defined, you have this non-commutative Hardy space, which consists of, well, a priori consists of all formal power series in these non-commuting variables. And the condition is that these coefficients should belong to little l2. Right? So in the non-commuting world, we don't have to worry about these weights, which is one of the nice things, but there are much deeper reasons why some things here are a bit easier. So Mike also explained that these are not just formal power series. You can evaluate them at certain matrices. Particularly, you can evaluate them at scalars, and at scalars in the unit ball. And then you get a map from the non-commutative Hardy space into the Drury-Arveson space, which you just get by taking an NC power series and evaluating it on the ball. And so Mike explained last week that this is a co-isometry, meaning it's a surjective partial isometry, or the adjoint is an isometry, same thing. And by the way, you can also take this as the definition of the Drury-Arveson space, because what you can do is you can just say, well, you look at the space of all holomorphic functions that you get by taking NC power series in the NC Hardy space, restricting them to level 1. And the norm you give it is the quotient norm, right? So the inf over all norms of NC power series that give you your given commutative power series at level 1. That's also a reasonable thing to do. So let me look at the reason for why this is this map is a co-isometry again, because I want to make a couple of points that are related to this. So one way to do it, which is essentially what Mike did last week, is to define something like a reproducing kernel for a point lambda in the open ball. So you look at this NC power series x to the w lambda bar to the w. This is in the NC Hardy space, and what it does for you is if you take an NC function f and you take the inner product against this little k lambda, then it reproduces the value of f at the point lambda. So it works like a reproducing kernel, at least at level 1. And then Mike also showed us this computation here, namely if you take the inner product of two of these things, so you get the sum, and then the reasonable thing to do is to group the terms in the sum so that you first sum over all words of length n, and then you sum over all n outside. And then you realize that if you sum over words of length n, this is the same as taking all possible products of mu I lambda I bar of length n, which, if you think about it, is nothing else than the inner product of lambda with of mu with lambda in c to the d to the n, right? Because if you take the inner product and you raise it to the power n and you multiply everything out, you get all possible products of length n. And then you have a geometric series, and this you discover again as the reproducing kernel of the Drury-Arveson space. So the point is that this reproducing kernel at level 1 of this NC-Hardy space, they have the same inner products as the reproducing kernels of the Drury-Arveson space. By the way, this is one place where NC things become a bit easier, because if you remember, we had a similar computation in the commutative world, but there the justification for why this thing or the analog of this thing equals this was a bit more difficult. We needed the multinomial theorem, right? And this is exactly what happens in the commutative world. In the commutative world, some of these things collapse, they turn out to be the same thing, but then you have to count. You have to count how many things are the same. Whereas in the non-commutative world, you don't care about which things are the same, because typically they're non-commuting, so they're not the same, and then you just have all potential products, which is actually a bit easier in this case. Okay, anyway, the fact that these inner products are the same here tells us that we get an isometry that takes the kernel in the Drury-Arveson space onto this kernel in the NC-Hardy space. And then if you take the adjoint of this isometry, this is the co-isometry that I mentioned earlier. So if you take a function in the NC-Hardy space, you can evaluate it at this point lambda by taking the inner product against a little k lambda. Little k lambda is v of big k lambda. You pull the v on the other side, and then you get the value of v star f at lambda. Okay, so one reason why I want to look at this again is because we have now this isometry from the Drury-Arveson space into the NC-Hardy space. So if you figure out what the range is, then you get a unitary from the Drury-Arveson space onto the range of this isometry. And so you could identify the Drury-Arveson space with a subspace of the NC-Hardy space. And I want to figure out what this subspace is. So this is why I wanted to look at this, this again. So up top, I've just written out the isometry again. So the crucial point here is, or the crucial definition is that of a symmetric power series. So a formal power series in non-commuting variables is symmetric, well, if it's invariant under permutations of the entries of the words. So what this means is if you have two words, W and W prime, and you can get W prime by permuting the entries of W in some way, then the coefficient should be the same. So then AW should be the same as AW prime. And you can see that everything in the range of this isometry V, so in particular these vectors here, they are symmetric because the lambdas are just scalars, right? So the entries of lambda, they do commute, and so they don't see if you permute the word or not. So these things, everything in the range of this V is a symmetric power series. And it turns out that this is exactly what you get. Oh, sorry, I had an example which I should have mentioned. So the baby example here is x1, x2 is not symmetric, obviously, because if you permute it, then you get x2, x1. But you can symmetrize it so that x1, x2 plus x2, x1 over 2, and then this turns out to be symmetric. Okay. The other example is there are these things in the range. And so this is exactly what you get. So V defines a unitary from the Drury-Arveson space onto the space of symmetric power series in non-commuting variables. And so one way to see that you get all symmetric power series is you can work out what V does on commutative polynomials. And so then you get all symmetric NC polynomials, and then in the limit you get all symmetric NC power series. Actually, let's look at this polynomial idea for a minute more. So if you have a commutative monomial, so something like z to the alpha, then in general, there are many NC monomials that give you your commutative monomial at level 1, so on scalars. In fact, you can count how, right? So in this example, you can see this. If you look at the monomial z1, z2, then you have two monomials that give you this, right? x1, x2, and x2, x1. And so in general, you can count how many there are. And the number of these monomials is exactly this weight that we've seen before, absolute alpha factorial divided by alpha factorial. And the reason is, if you look at z to the alpha, this is a product of length absolute value of alpha. And so you have that many factorial permutations of it, but then you overcount it, because if you just permute the x1s among each other, then amongst themselves, then it doesn't change. So you have to divide out by alpha 1 factorial. And then if you just divide permute the x2s among themselves, you overcount by a factor of alpha 2 factorial. So you get this, this weight here. And then it shouldn't come as a big surprise that this map V takes a commutative monomial z to the alpha and sends it to the average over all non-commutative monomials that agree with your given commutative monomial at level 1. So one way to see this formally is you can look at this definition up top here, and you expand both sides in the power series in lambda, and you compare coefficients. And if you compare the coefficients, this is exactly the formula you get. So this is another way to explain where these coefficients or these weights in the definition of the Drury-Arveson space come from, because they are precisely the number of NC monomials that give you your given commutative monomial. So that's another way of seeing it. Okay. Let me make a quick aside here. So the this point of view of the NC Hardy space and that they're really non-commutative holomorphic functions is somewhat recent. I think it's an extremely helpful point of view. But there's another point of view which you can also see in some of the older literature, and this is Fock space. So I want to briefly mention this to also explain why this space is sometimes called symmetric Fock space. So the full Fock space over C to the D is the space you get by taking all tensor powers of C to the D, and then you take the L2 direct sum of those. So right, so each E to the tensor n is a Hilbert space, and you can take the L2 direct sum of those. And the point is that this is really just this NC Hardy space in disguise, because you can identify the NC Hardy space with this full Fock space just by identifying a non-commutative monomial with the corresponding tensor of basis vectors. So the way that this works is, for instance, if you have x1, x2, x1, then this gets mapped to E1 tensor E2 tensor E1. And then you can extend this by linearity. And there's an argument to be made that it's slightly more natural to make it conjugate linear as opposed to linear, because, for instance, if you look at what happens at degree 1, then in the NC Hardy space, you get homogeneous polynomials of degree 1, and in the full Fock space, you get just vectors of C to the D. And so the natural thing is that polynomials of degree 1 are linear forms on C to the D. But anyway, it's not so crucial for what I'm going to talk about. It's you can also make it linear if you prefer that. So we had identified the Drury-Arveson space as a subspace of this NC Hardy space, namely the symmetric power series. And then on the other side, on the Fock space side, you get what are called symmetric tensors. So you can imagine what the definition is. And this gives an identification of this Drury-Arveson space with symmetric Fock space. So this is just the set of all symmetric tensors in this full Fock space. And so this was, for instance, Arveson's point of view in his 98 paper. So this is why people sometimes call it symmetric Fock space, because you have this identification here. Okay, so let me summarize what we've seen so far. So we've seen many different descriptions of the Drury-Arveson space, and so here I'm just summarizing them again. So first you can define it using power series. You can say it's all the power series or holomorphic functions, if you like, so that the Taylor coefficients are in some weighted L2 space, and the weights are these things that we've seen many times now. You can describe it in terms of the reproducing kernel. The reproducing kernel is the sort of most obvious generalization of the Hardy space kernel you can think of. We had a function theory description, which roughly says if you take dimension over 2 radial derivatives, then you should be in the Bergman space. And there is this NC characterization, which says it's precisely what you get when you take functions in this NC Hardy space and restrict them to level 1. Or alternatively, it's the same thing, it's symmetric Fock space. So this is one of the reasons why the theory is so rich, because there are all these different points of view. And depending on your particular problem, the different points of view can be more useful or not, or more useful than others. And so often choosing the right point of view is sort of half the battle. And as you can imagine, so this power series and RKHS point of view is useful if you want to use Hilbert space arguments, and if you want to use operator theory or operator algebras. And something similar can be said about the NC point of view. And this function theory point of view is quite useful if you actually want to do, explicit estimates, harmonic analysis, and so on. And so the fact that we have these different approaches to these spaces, to this particular space, has made for a very rich theory. Okay, so I think this is a good place to stop for today. So tomorrow I'm going to talk about why this space is actually interesting from the point of view of operator theory, and I'm also going to talk about multipliers. But for today, that's it.
Thanks a lot, Michael. Let's thank the speaker first. Any question or comments? I think Marco started with something in the chat. Do you see it, Michael?
Yes. I believe so, but maybe someone who has worked on the classical Hardy space more than I have wants to chime in.
I don't think they're the same as the harmonic majorant ones on the ball. Because in Rudin's book, he's got these Loomer Hardy spaces, which are defined by harmonic majorants, and my dim memory is that they might be different, but I would have to look in the book. But Rudin's book on function theory of the unit ball treats that, but I think they're different.
Okay, thanks a lot.
Further question or comments?
Sure. I'd like to make one comment. I mean, I guess this will come out, maybe it comes out in tomorrow's talk, but the von Neumann inequalities for row contractions that Drury proved and then Mueller and Vasilescu proved and generalized, both of them only recognize this space in the first version, the power series. But that's probably the least useful one because you don't recognize it as an interesting space, whereas all of the others, have proven pretty important for various ways of attack. So, just sort of proving the theorem and saying, okay, you've got a universal model, which is a bunch of weighted shifts, didn't turn out to catch people's attention. It wasn't until these other connections were made that people got interested in the space.
Yeah, I think Arveson was, as far as I can tell, the first one to actually realize that it's a reproducing kernel Hilbert space with a natural reproducing kernel and this connection to symmetric Fock space and so on.
That's true, I think.
Thanks, Ken, for explanation. Further questions or comments? Somebody asked for, I think it was in chat. Yeah, Fuad asked for the slides. You can share it today or last day.
How about I give you the slides at the end, and then I can give you sort of the final version of the whole thing, if that's okay. And
that would,
does that work?
Yeah, perfect.
Okay, thanks.
Thank you. Let's thank Michael again.